with doing the Lewis dot structures, right? So you basically have everything you need now to do most of the Lewis dot worksheet. The last piece is going to be this, and so hopefully you've done most of that already. You can go in and you can just fill in these structures based on the information you've already got. Because today's topic, we're going to be talking about why, or really how, the electrons around a atom, and in particular the bonds, combination of bonds and electrons, gives them their 3D shape. So the core to this, in Lewis theory, is the valence shell electron pair repulsion theory, which, if you were to read it out, you'd probably say Vesper, but I like Vesper. It's way easier to say. And essentially this is the electrons repel each other, and so they get as far apart as possible. So in like this molecule right here, we'll talk about it, it's a tetrahedral. I actually have this too. And then you can get other shapes. So like this model. CCl4. So this is also a tetrahedral. All right, we've got 4 chlorine atoms all attached to a carbon. And as we'll see, anytime you have 4 atoms attached to a central atom, you'll get this shape. And that's like the optimal spacing of everything in that molecule. So that's all valence shell repulsion theory. The real critical things here are that electron groups repel each other, and that each of these things in this list here counts as one electron group. So I'll be abbreviating this as EG, and those are lone pairs, single bonds, double bonds, and triple bonds. So if you had something with 2 double bonds, those would each count as 1 electron group. So you'd have 2 total electron groups. So it's kind of a simple theory, but it works. So spread everything out as much as possible. First one we're going to look at is carbon monoxide. Actually, do I have the ones? Yeah, I can make carbon monoxide. So we talked about double and triple bonds too. I don't think I have all the right. Oh, I do. So black is usually carbon, red is usually oxygen. So this will be carbon monoxide, right? It's just a straight line. And so when we have these 2 electron groups, the farthest they can get away from each other is on opposite sides of the carbon, or whatever the central atom happens to be. It doesn't have to be carbon. So that's a linear geometry with a bond angle of 180 degrees. So all the way around on the other side. This molecule is formaldehyde, and it has 3 electron groups around the central atom. It's like depends on if I can find. I don't have one that can just do 3 electron groups. So in this case, though, you can imagine taking this, and then if you added another group on top here, then these 2 would have to spread out a little bit. So you'd kind of divide it equally into thirds. So in this configuration, where you've got 3 electron groups, they'll spread out into this flat trigonal planar geometry. So tri meaning 3, trigonal, actually I don't know what the suffix gonal means, but planar meaning that it's flat. So you could take this shape, you could set it flat on a table. And the bond angle between those is 120 degrees. When we go from 3 to 4 is where things get a little different, because we can no longer just spread out flat in 4 directions. For example, this is usually how people want to write these out. All right, so if we add 4 groups, if we kept the molecule flat, they would form like this cross, right? So that would put them at 90-degree spacings. but it's also not using the sort of space in front or behind that central carbon. So that's why this is actually the shape that we get, which is called a tetrahedral. So this would be square planar. This is wrong. The tetrahedral shape is what we get. And so it forms this triangle, or not really a triangle, so it's a tetrahedral geometry. Our bond angle, as you can see, is 109.5, which is larger than the 90-degree bond angle that we would get here. So there's more space between them. And it makes a geometric shape with 4 triangular faces. So you can zoom in on this guy. You see that there's a triangle face here, then there's one on the back, and then one on the bottom. And each of those hydrogens forms a point on that triangle. Okay, so that's when we've got groups that have atoms on them. Things change a little bit when we start removing those atoms and replacing them with lone pairs. So for ammonia, there are 4 electron groups. Because remember, lone pairs, single bonds, double bonds, and triple bonds each count as a single electron group. So we have 4 electron groups, but now one of them is a lone pair, and 3 are bonding pairs. So bonding pairs is anytime we have electrons between, well, forming a bond between 2 different atoms. And so we have to differentiate between the electron geometry, which is just the arrangement of electron groups. So that would still be tetrahedral. But now we also have a molecular geometry, which is not talking about just the electron groups, but also is there something attached to the end of those electron groups? So that lone pair exerts an influence just like if we did have another hydrogen there. And so this gives us a different shape of, trigonal pyramidal. Okay, so that's if we remove one of our hydrogens, essentially. What happens if we remove 2 of them? We have the same electron geometry because we still have 4 electron groups. So anytime we have 4 electron groups, it's going to be tetrahedral. Anytime we have 3 electron groups, it's going to be trigonal planar, and anytime there's 2, it's going to be linear. But here we have 4 electron groups, with 2 lone pairs and 2 bonding pairs. So the molecular geometry ends up being bent. All right, so it forms this V. Rather than being a line, it's bent. So still, electron geometry is tetrahedral, molecular geometry is bent. So both of those lone pairs, and really actually all of the lone pairs, arrange themselves as if there's still 4 groups, because there are still 4 groups. We just draw a distinction between whether or not there's bonds to other atoms. So the easy way to look at all of these is to use this table, because you can count the number of electron groups, count the number of bonding pairs, and you count the number of lone pairs. So if we go back to something like water, so imagine that this one's water, we have 4, we'll do it this way, we're going to have electron groups, we have 4 electron groups, because we have 2 bonds, 2 lone pairs. Then we have bonding groups. We have 2 bonding groups, so those are where the hydrogens are attached. And we have 2 lone pairs. So when you use this table, all you have to do is say, okay, I've got 4 electron groups, and that's the first column. So we can't have 2, 3, or 3. It's not going to be any of those. So we're going to be one of these 3. And then we say, how many bonding groups do we have? It's not 4, it's not 3, it's 2. So really, you only need the number of electron groups and the number of bonding groups, and then you can figure out which shape you have. So water will have a tetrahedral electron geometry and a bent molecular geometry. And I will put this table on the exam. You just have to know how to use it. So when we're trying to predict geometry, right, whether it's a trigonal planar, tetrahedral, bent, or linear, the first step is to draw a correct Lewis structure. So on an exam, I would give you a question that would be like, draw the Lewis structure for this and predict the geometry, just like it is on the Lewis dot structure worksheet. So you got to first draw the correct Lewis structure. So getting all of those electrons, arranging them, figuring out how things are bonded correctly to get 8 valence electrons. Then you count the total number of electron groups around the central atom, and that's the key. We're always going to be doing it for the central atom. We don't get any more complicated than that. And then you want to determine the number of bonding groups and the number of lone pairs around that central atom. And then you can just come back to this table and look up what your shape is. So I need to bookmark that page. Okay. So our first step, if we want to predict this, I don't know what this molecule is called, chlorine nitroxide maybe. So we're going to have chlorine, and we're told that nitrogen is the central atom, and that oxygen, then chlorine and oxygen will be our terminal atoms. All right, so then we got to figure out how many valence electrons we have. So we've got chlorine, nitrogen, oxygen. How many valence electrons does chlorine have? 7. Again, it's in column 7A, or 17 on these periodic tables, so it has 7 valence electrons. How many does nitrogen have? 5, thank you. And oxygen? 6. So then we can just add all of those together. We'll get 18 electrons. So then our next step is to place our minimum number of bonds. So one bond between chlorine and nitrogen, and then another between nitrogen and oxygen. And so that's taking up 4 of our total valence electrons. So we'll subtract those from our total valence pool to give us 14 electrons left over. Bless you. And then we can take those remaining 14 electrons and we'll distribute them around our terminal atoms first and then our central atom. So we have 2, 4, 6, 8, 10, 12, 14. So at this point we have to count and make sure that we have a correct Lewis dot structure. So for chlorine we've got 2, 4, 6, 8 electrons. For oxygen, it's 2, 4, 6, and 8. But nitrogen only has 2, 4, 6. I would not expect you to know this, but in this case, we should be taking the double, or taking a lone pair from oxygen. Whoops. To make that double bond. So if you did it from chlorine, that would be fine. I wouldn't count that against you, because we haven't covered anything to help you determine that.
It doesn't break a lot though, right? What you were talking about?
No. No, it comes down to oxidation states, and yeah. It's a Chem 1 thing. So for now, just trust me, oxygen's the right one to do here. But again, if you did chlorine, made that double bond between chlorine and nitrogen, it would be fine. But we do need a double bond here just because nitrogen doesn't have enough valence electrons. So by borrowing or sharing a lone pair from oxygen, we can complete that octet. Okay. So now this is the correct Lewis dot structure. Everything's got 8 valence electrons. Now if we want to determine the molecular geometry, we need the number of electron groups, we need the number of bonding groups, and we need the number of lone pairs. and again for our central atom. So how many electron groups does nitrogen have? 3. Yeah, it does have 3. Because we count single bonds as one electron group. We also count double bonds as a single electron group. And then we count lone pairs as an electron group. So we got 3 electron groups. And then how many bonding groups? Just 2. So our bonding groups follow the same rules as electron groups in that each of those bonds just counts as one bonding group, whether it's a double bond or a triple bond. So then how many lone pairs do we have? 1. Yeah, just 1. And our bonding groups and lone pairs will always add up to the number of electron groups.
So the lone pair, is that what we got rid of from oxygen? Is that the lone pair?
No, the lone pair is this pair of electrons.
Oh, okay.
Yeah. The electrons that are all alone, they don't have a bond. And a lone pair. Okay, so if we have 3 electron groups, 2 bonding groups, and 1 lone pair, what is our molecular geometry? Yeah, so we go to 3. There's 2 options for 3, but there's only one that has 2 bonding groups. So our molecular geometry would be bent. Our electron geometry would be trigonal planar. So the electron geometry is only dependent on the number of electron groups. You can see here that if we have 2 electron groups, that's going to be linear electron geometry. 3, those are both trigonal planar. And if we have 4 electron groups, those are all tetrahedral. Okay, so we got, come back over here. So our molecular geometry is bent.
On the worksheet, you want us to both the molecular and electron, or?
Just the molecular geometry. Yeah.
When you have it set up like that, when it's just straight across, could you already predict just from looking at it that it's going to be linear or bent?
Yeah.
If there's no it's just between those two, right? When it's like structured like that.
Right. So yeah, I think the table is super helpful if you have a hard time like creating like a 3D thing in your head. Some people are better at that. Some people are worse. So like for me, I like visualize a tetrahedral, and I can just like pick one of the atoms off, and then get the shape.
Yeah.
But I also have like 10 years of experience doing this kind of thing. It's been that long since I took Chem 1.
Are we going to get that chart on the test, or doesn't it memorize?
No, I will give you the chart. You just have to know how to use it. Yeah, I will give you that chart. All right, so you're going to help me out more with this one now. If we have sulfate, we want a Lewis dot structure. What do we do first? Skeletal structure? Yes. So how should I put those? S in the middle? Yeah, oxygen's around it. Nice. All right, what's next? It depends. We could do minimum bonds here. I think it helps to do valence electrons, then minimum bonds, and then subtract those out. But we'll do valence electrons first. Okay, so we got sulfur. There's just one of those. And there's oxygen. Not one of those. There's 3 of those. So sulfur and oxygen are both in 6A. So they have 6. Column 16. So 24 electrons there.
You have to add 2 to that?
Yes, thank you. We have to add 2 more because we have a 2- charge. So we'll add another 2 electrons here. Okay. Yep, now we add our bonds. There's just 3 of those, so that's another, we'll take off 6 electrons. Good, good, good. So where do we put those 20 electrons? Yeah, we'll do the oxygens first. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So do we have a correct Lewis structure? Did I not place 2 electrons? I'll double check. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we got all our electrons. Everything has, right, oxygen has 8, sulfur has 8. So it should be good. This should be the Lewis dot structure. Technically, we do also want this to show that the overall thing is an ion, and then it has a 2- charge. All right, so how many electron groups? 4. How many bonding groups? 3. And then just 1 lone pair. So we've got 4, 3, 1. So that makes our geometry what? Yeah, because we got 4 electron groups, 3 bonding groups, 1 lone pair. And so our electron geometry would be tetrahedral, but our molecular geometry is trigonal pyramidal. Whoop, that was weird. Trigonal pyramidal. It's just another set of steps to memorize. Okay. When we're drawing these geometries out on paper, it's hard to show that this is the shape that it is. The way we end up doing it is that we put part of this in line with the paper. And so that's the straight line. So here we're looking at a tetrahedral. So just to arrange this like that tetrahedral. Put these back on here. Kind of looking at it from this angle. But in order to see both of these, it's kind of like looking up at it from an angle. So we've got our hash lines, which are projecting into the paper. So imagine the piece of paper is here. There's one of these that's inside the paper or behind it. And then there's a wedge, so that's this one coming out of the paper. I'm not going to expect you to be able to read these kind of things, but it's a good thing to be aware of. That when you see these dashes, hash lines, and wedges, that's indicating the 3D shape of the molecule.
You're not making us draw it like that, or you are?
No. No, I'm not going to make you draw it like that. Okay, so figuring out how these things form 3D shapes is a precursor to polarity and electronegativity. So why don't oil and water mix? Comes down to something about the water molecules and something about the oil molecules, which does end up being polarity. But why? So if we have oxygen and hydrogen atoms, each donate 1 electron to the covalent bond between them, but they don't share these electrons equally. In fact, oxygen hogs most of those electrons. So if you were to draw this out sort of on a continuum between oxygen and hydrogen, those electrons would actually be more like that. And more accurately, we draw those as clouds. So that you would have a small cloud around hydrogen, and then a larger cloud around oxygen. And that unequal sharing means that oxygen in this case is more negative, right? Because electrons have negative charge. If those oxygens are hanging around oxygen, or if the electrons are hanging around oxygen, then it's more negative. And the hydrogens are actually slightly positive. So we get this difference in charge, and opposite charges attract. So if we had another, let's put our oxygen this way, and it's got hydrogens over here, and that's, again, unequally sharing its electrons. This one's going to be slightly negative, and this one's going to be slightly positive. So they end up sticking together. And kind of like these all, actually very similar to this, because these are ionic bonds, so they're transferring those electrons completely. So each of the sodiums is positively charged, and each of the chlorines is negatively charged. The shape of water molecules is different, but they're lining up like this inside of water and able to flow around each other. So those electrons are more likely to be found near the oxygen rather than the hydrogen. And this is called electronegativity. So how much any particular atom hogs those electrons, those shared electrons, is its electronegativity. We use a relative scale, and everything is relative to fluorine. So fluorine is just kind of given an electronegativity of 4. And then all of the other elements in the periodic table are less than fluorine. It wants the electrons the most. Here's a better picture than my scribbled one. So we've got our oxygen here on the left and the hydrogen on the right. You see that the electrons are spending more time around oxygen than they are around hydrogen. And again, we use this delta to signal a partial positive or a partial negative charge. So these are called dipole moments. So we have this difference in charge. It's called a dipole, right? There's di meaning two poles. There's 2 poles to the charge. So we've got different types of covalent bonds then, depending on how much those electrons are shared or are not shared. If we have a covalent bond that has a dipole moment, those are called polar covalent bonds. All right, so we've got dipole moment, we've got a polar bond. It's a bond that has 2 poles. So this is caused by if there's a greater electronegativity difference, you're going to have a stronger dipole moment. We'll see some examples of that. Actually, I'll do them right here because we've got this table. So hydrogen has an electronegativity. Is that just impossible to read? It's pretty bad. So hydrogen here has an electronegativity of 2.1. You can still kind of tell based on the heights of these things. Fluorine is 4.0. Fluorine, hydrogen. Oxygen is 3.5. And something like carbon is 2.5. So if there's a difference in electronegativity, the electrons will be unequally shared. So if we have something like hydrogen bound to carbon, hydrogen is 2.1, carbon is 2.5. So the difference is almost 0. It's very, very small. So they're actually going to be very equally sharing those 2 electrons. So there would not be a dipole moment there. If we instead had hydrogen and oxygen, now our difference is, let's put oxygen next to this, carbon here, 3.5 for oxygen and 2.1 for hydrogen. That's a lot bigger of electronegativity difference than between carbon and hydrogen. So most of these, wrong one. Most of these electrons are going to be, the electrons are going to be spending more time around oxygen, not hydrogen. And then if we go even further, we can do hydrogen and fluorine. So now our difference is even bigger. The electrons are going to be spending even less time around hydrogen. The electrons will spend less time around hydrogen and way more time around fluorine. So like we saw with the carbon and hydrogen bond, if that difference is small, there's not going to be a dipole moment, and so there's no poles. It's a nonpolar bond. So nonpolar covalent bond. And then any bond between two atoms of the same element is going to be nonpolar because they have the exact same electronegativity, so they're going to be very equally sharing those electrons. If you get a really large difference in electronegativity, you get a complete transfer of those electrons. So the difference in electronegativity between sodium and chlorine, let's go back and check. Sodium is 0.9, chlorine is 3.0. So this is 0.9, 3.0. It's a massive difference. And so those electrons won't be spending any time around sodium, and they'll spend all of their time around chlorine. So kind of the two opposite ends of the spectrum is the nonpolar bond versus the ionic bond. And then everything in between, those are polar bonds. So intermediate electronegativity is a polar covalent bond. So you get a lot of those between nonmetals. And this is the rule of thumb for determining if you have a nonpolar, a polar covalent, or an ionic bond. So anything from 0 to 0.4 is going to be a pure covalent. We also call it a nonpolar. Then going from a difference of 0.4 to 2 would be a polar covalent bond. So even hydrogen or hydrofluoric acid, this HF bond is going to be polar covalent. And then anything larger than that, you just get a complete transfer of electrons. And so those are ionic bonds. Okay, so is the bond formed between each pair of atoms pure covalent, aka nonpolar, polar covalent, or ionic? So we have a bond between iodine and iodine. Nonpolar. Nonpolar, pure covalent. How about for cesium and bromine? Just think about it without switching back to the other slide. Where's cesium on the periodic table? Mm-hmm. And bromine's all the way on the right. It's going to be an ionic bond. All right, so all of our compounds that we've named that are between metals and nonmetals are ionic compounds. They have ionic bonds. So you can go look at the difference. Let me find the difference though. So cesium is 0.7, bromine's 2.8. Oops, too far. So 2.8 minus 0.7 would give us a difference of 2.1. All right, so that's for a rule of thumb, greater than 2, we're going to have an ionic bond, as well as just being able to look at the periodic table and know that it's an ionic compound. Phosphorus and oxygen, though. So phosphorus is 2.1, oxygen's 3.5. So if we have 2.1 or 3.5 minus 2.1, we have a difference of 1.4. Yeah. So this would be polar covalent. And this one was ionic. So again, it's 0 to 0.4, and then 0.4 to 2.0, and 2.0 plus would be pure covalent, polar, and ionic. All right, so going from polar bonds to polar molecules. Polar bonds don't necessarily mean that you have a polar molecule. Because a polar molecule has a net dipole moment. So that means when you look at the whole thing, there's one side of that whole molecule that's negatively charged, or one side that's positively charged. So if you have a diatomic molecule, again, that would be something like hydrogen and fluorine. This is a polar bond, and there's only 2 atoms. So we have an overall dipole moment that makes that a polar molecule. But for other molecules, if we had 2 or more polar bonds, let's just say we had, carbon tetrachloride. Plus again, that's this shape. So each of those bonds individually is polar, but they're all pulling at directly opposing angles away from the central carbon atom. So our overall dipole moment is 0. You can kind of think of this, well, a more simple way to think of this is playing tug of war. So if you've got carbon dioxide, where we've got just the 2, 1 oxygen on each side, each of these bonds is polar, but if you imagine playing tug of war with this, pulling on this side and pulling on this side with the equal force is not going to move it anywhere. So this is nonpolar. If one of these was something else and had a stronger dipole bond, then it would be polar. We'll get to some more examples. So we can represent our polar bonds with arrows or vectors that point in the direction of the negative pole and have a plus sign at the positive pole. So we have carbon, do carbon dioxide again. Let me switch colors. I think this one shows up. So here our dipole moment, the oxygen's more electronegative than carbon, so it's going to have the negative. And then, oh wait, I did that the wrong way, this way. So the arrow is going to point out, and the positive end is going to be the tail of that arrow. And then we'll have exactly the same amount of dipole moment on the opposite side. Let me do a better job. All right, so those 2 arrows are identical in pointing in opposite directions. So if vector math is your thing, you can think about it like that. So if you get something else like water here, now our shape has even more than just the polar covalent bonds. So we've got the 2 polar covalent bonds down here. So if I pull on both of these at a down and outward direction, the overall force is going to move this down. So this is a polar molecule. And even more than that, it's got 2 lone pairs on top. But so you can see how these arrows are not directly opposing each other. So we have a polar molecule. I think the other one that still kind of makes sense intuitively is when we have a trigonal planar. So now we've got one, oh, sorry, I don't have one to make this. So if we had a rope that's split 3 ways, and we spread each of those people out, or each of those groups out in 3 different directions, and I meant to bring a rope, but I forgot, all 3 groups could pull with equal force and not go anywhere. because the two groups over there would be pulling against the group over here, and vice versa all the way around. So they're all pulling in opposite directions. And then the same thing kind of applies with a tetrahedral. So again, looking at this with all the hydrogens on it. All of these groups are pulling with equal force away from the center. And they're spaced perfectly evenly, so that force is identical in all directions. So if you can imagine multiple groups playing tug of war in your head, that's a fine way to do it. That's pretty hard to do. So you can also look at this another way. Well, this is more of that. So you determine whether molecule contains polar bonds. So the two bonding atoms have different electronegativities. And then determine whether the bonds add together to form a net dipole moment. So if you have perfect symmetry like this would be nonpolar. So we have our tetrahedral, and then they're all hydrogens. If I swapped one of these out with oxygen, now oxygen and carbon are going to have a net dipole moment, and that's going to be different than the other three hydrogen bonds. So now, while looking at it straight on, it might be symmetrical. We have an asymmetry in this plane, where this is now going to be very negative, and the rest of this is going to be kind of positive. So you've got two poles, positive end, negative, or negative end, positive end. The other way you can do this, though, is if you use the molecular geometry and electron geometries. You can look at the Lewis structure for the molecule. So let me do water. So we got water and then two lone pairs. Okay, so our molecule will be nonpolar if both of these things are true. There are no lone pairs on the central atom, and the atoms bonded to the central atom are all the same. So is water polar or nonpolar? Well, the first one here is that there are no lone pairs, and we have two lone pairs. So water's polar. If I redraw this, if I draw methane. Okay, let's look at our first condition here. There are no lone pairs on the central atom. We're good there. Carbon doesn't have any lone pairs. And then the atoms bonded to the central atom are all the same. So all of these bonds are hydrogen. So this would be nonpolar. And even simpler if you flip this and think about if there's a electron, if there's a lone pair, it's polar. There's a lone pair on the central atom, and we've got more than two atoms, it's going to be polar. So let's look, well, I just did this example, of course. So CH4, actually here, let me change this up. Let's make this oxygen. And let's make this guy. So this is no longer CH4. This is CH2O. So for this molecule, just giving you the Lewis structure here, is it polar or nonpolar?
Nonpolar.
Why do you say it's nonpolar?
The rules you just said, they all have to be the same atoms, and then oxygen is a different atom, and then there's lone pairs too.
Well, it's nonpolar. Oh, I see what you're saying. Yeah, there are lone pairs here. Usually it's lone pairs on the central atom, but that doesn't make you wrong in this case necessarily. Because you said nonpolar? So for the nonpolar rules, it's no lone pairs on the central atom. So we've got no lone pairs. But the atoms bonded to the central atom are not all the same here.
Yeah.
So both of these have to be true to be nonpolar. So this is true, 1 is true,
Oh, okay.
but 2 isn't true. So this one is polar. How about if we did this one? Is this polar or nonpolar?
Nonpolar. They'll have the same force.
Nonpolar. So we do have lone pairs on our terminal atoms, but there's none on our central. And then these are all the same out here.
If one of them had more lone, well, it couldn't have one.
Yeah, one could be more electronegative than the others.
So let's say one of them had, like, let's say all of them had 4 and then one of them had 6 lone pairs. Would that one be more?
It's not possible to make that, but I think yes.
Okay.
Yeah. I don't know if we did this one already. Is this one polar or nonpolar? Why do you say nonpolar? So we've got no lone pairs, check. But one of these is different than the other two. So that would be polar. Sorry, this is polar, nonpolar.
Okay. You're looking at the central atom to figure it out?
Yeah.
Oh, okay. That makes more sense.
Let's try one more. Kind of ran out of space there. Actually, hold on. We got another example. Let me rewrite that over here. Is that polar or nonpolar? Well, we've got no. It is polar. Yeah, we got multiple groups that are not the same. Yeah. All right, let's do. Oh, this is good. This will change it up a little bit. I want to get into chapter 11, so I'm going to just. So is this polar or nonpolar? We have lone pairs. It's polar. So really, anytime you have lone pairs, so the only time that you would have lone pairs on one of the central atoms and it would be nonpolar is when you've got 2 of the same. Wow, I did that backwards. So this is nonpolar because this bond between these two is nonpolar. So there's no dipole moment one way or the other with this. Maybe I should have done more of that here. So here, this is going to be an overall, we do it in a different color again. Overall dipole moment going in that direction. So the negative is going to be with that lone pair, and then the positive is going to be on the hydrogens. Okay. Yeah, this is a good one too. Let's actually go through the process for this one. So we'll do our skeletal structure first. And how many valence electrons are we going to have? 18. So we'll do our bonds. 14 electrons. And then we can distribute these. 2, 4, 6, 8, 10, 12, 14. Which side should we take a lone pair from? You take it from either. Yeah, because this would be a resonance structure. So you could do either one. Oops. I'll do the right side though. Okay. Now is it polar or nonpolar? Polar. It's polar because we have a lone pair. Yeah. So if you have a lone pair and there's more than 2 atoms, it's polar.
I'm just a little confused. Where did you pull the 4 electrons expected to?
Oh, that was the 2 bonds.
Oh, okay.
Yeah, this one, right?
Yeah.
Yeah. Yeah, that was placing the minimum bond. So it was. Yeah, so this would be polar. All right. So the reason that oil and water don't mix is that when you have polar bonds, like I was saying before, kind of like this, they line up all together, and then they're attracted to each other because of those opposite charges. And so they snap together like magnets. And when they snap together like that, they actually push out all of the oil molecules. Because the oil molecules don't have a bond, the nonpolar oil molecules don't have a dipole moment, and so they don't fit into they don't stick to any of the other things. So then if there's an oil molecule in the middle and the 2 water molecules opposite it, they're going to push past it and squeeze it out. So because the interactions between polar and nonpolar molecules is very, very weak, they end up just getting excluded from the mix. So if you had, I think you could buy magnetic marbles. Sounds really cool. So if you had a mixture of magnetic and non-magnetic marbles, and you threw those all together, all of the magnetic marbles would clump up, and they would push out almost all of the non-magnetic marbles. So those are the non-magnetic ones out here, and then these are the magnetic ones all bunched up. So then if you look at this, all of these water molecules are all actually lining up with each other, positive end to negative end. And then the oil molecules can't fit in between any of those spaces. And this is why we have dish soap, because dish soap is both polar and nonpolar. So when you put soap on something, the nonpolar tail sticks to the grease, and then the polar end gets carried away by the water, taking the grease with it. And if you mix oil into water, add soap, and mix it up, the soap bubbles will form like little, well, if you're familiar with biology, it's the phospholipid bilayer is polar on one end and nonpolar on the other, and it forms a micelle. Micelle? I think that's the right word. So you can form these little bubbles of grease inside of the water. All right, that is it for chapter 10. Are there any questions about polarity stuff? I'm trying to remember. I think there's a simulation thing if you want to look at it. I'll try and find it and post it.